Good morning, children. I hope you have seen my earlier video of electric field and electric dipole moment. Let us revise these two terms again. Electric field is defined as force per unit positive charge placed at a given point, and electric dipole moment is defined as the product of either charge and distance of separation between the charges. So that is the electric dipole moment. Then we have also studied how to find an electric field on the axial line of a dipole. The axial line is a straight line and we consider any point on that straight line. Due to dipole, we have to find electric field at a particular point on the axis of the dipole. So that also we have studied. Now to further the study, we have to study the electric field on the equatorial line of a dipole. What is an equatorial line? Equatorial line is nothing but the perpendicular bisector. So if you have a dipole, we have two charges, plus q and minus q, and then we draw a perpendicular bisector. Take any point on the perpendicular bisector and find out the electric field at that particular point. So let us study how to find electric field on the equatorial line of a dipole. Here you can see, today we will study the electric field on the equatorial line of a dipole. So let us first draw the electric dipole. Consider electric dipole minus q charge at this point and another one, that is the plus q charge at this point. Let this point be A and this point be B. As you know, the center of the dipole is marked as O, and we draw one perpendicular bisector. So let me consider the perpendicular bisector here and consider the point P. At this point P, we are interested in finding the electric field that is on the equatorial line of the dipole. Let this point P be at a distance r from the center. Now I have to join this to point A because we have to find electric field at this point due to the charge minus q. Similarly, I have to join this point P at P and B, so that we get the distance between P and the point B. At point B we have the charge plus Q. Now the electric field due to minus Q charge at A, so that we will call as EA, and that is nothing but we have studied the formula KQ by R square. Now R is the distance of point P from A. So as you can see that this distance is A and A, the length of the dipole is 2A. So this distance will be from the center, so it is A. Now you can use the Pythagoras theorem and write this distance as square root of R square plus A square. The distance from P to A, point P to A, it is root of R square plus A square. So our formula is KQ by R square. Now R square is square root of R square plus A square. So when we take the square root of R square plus A square, we will get only R square plus A square. Now at this point we are interested in finding the electric field due to minus Q charge. So we consider a test charge here. So test charge will experience a force. You must be remembering that we find the force on the test charge. So consider a test charge placed at point P. So this is a plus charge, this is a minus charge. So what will be the direction of this charge? Obviously it will be towards this minus Q charge. Now this electric field is EA, which we have written here. The magnitude is written here. I am showing the direction as EEA. Now similarly for point B, we have the plus Q charge at point B and we are finding the electric field at point P. So it will be called as EB. And that is again the same because here also we get the under root of R square plus A square because this is A and this is R. So this is again by Pythagoras theorem hypotenuse, and you can get it as square root of R square plus A square. So now electric field at point B, K into Q upon R square plus A square. Electric field. What is the direction of this electric field? Now again for final, the test charge is plus, this charge is plus. So what will be the direction of force on plus Q charge? So since this is a repulsion, so it will be having the force in this particular direction. So I have drawn it in this direction, in the upward direction. Now you can see that the magnitude of both EA and EB is same. EA is equal to EB. Can you write like this? EA is equal to EB because both are having same. So electric field due to A is equal to electric field due to B. Only the directions are different. EB is along this direction, EA is along this direction. Now our task is to find the net electric field, which is, you can see the vector addition of these two. Now this angle we have taken as theta. This angle is also theta. So now if I find out using the parallelogram law, I will get this as the resultant vector. So this angle is theta, this angle is also theta. So I can write all this in the given diagram. Now to find the net electric field E, which is acting in this direction. The net electric field due to EA and EB is along this direction. You can write this direction as, say, PX. So it is in this particular direction. Now to find the electric field E, what we can do is, we can take the resolution of vectors. Because you can see one vector is in this direction, so we can resolve it along two directions. Let me resolve the two vectors EA and EB. Now you can see that this vector which is here, it is resolved into two directions, EB sine theta, which is along the perpendicular, and along this direction the EB vector which was resolved, it is EB cos theta. Now similarly, this vector is EA. This is also resolved along two components. This component is EA . Now let us see how to find the total electric field at point P. E is equal to 2A cos theta. Vertical components are getting cancelled and we are getting only the two horizontal components, EA cos theta plus EB cos theta. Since both are equal, we can write E is equal to 2A cos theta. Put the value of EA, KQ by R square plus A square. Put the value of cos theta from the triangle as base upon hypotenuse, A upon root of R square plus A square. A cos theta is A base upon under root of R square plus A square. Solving this, we can write Q into 2A as P. So we get the final formula, E equatorial is equal to 1 upon 4 pi epsilon naught P upon R square plus A square raised to 3 by 2. So this is the final expression. So I hope you have understood how to derive the formula for electric field on equatorial line of a dipole.